So a complex number, okay, we're going to try and just fill in some blanks here. A complex number is in the form of a plus bi, okay? That's the standard form of a complex number, right? The I is an imaginary number. So this you should be familiar with from Algebra 2, right? So I is actually equal to what? The square root of -1, okay? So I always have people say, well, why do we have to use I? Well, we have to use I because the fact is the square root of negative numbers does occur. So there has to be some way of handling that, okay? So I squared, well, that would be the square root of -1 times the square root of -1, which is -1. Okay, so we have I, which is the square root of -1. I squared is -1. I to the third, well, that's I squared times I, which would be -1 times I, which equals -I. Okay, it looks complicated, but it's actually very, very simple. You just have to remember I is the square root of -1, right? I to the fourth, well, that's I squared times I squared, which is -1 times -1, which equals 1. Is this looking familiar? Okay. I to the fifth, well, we could say that's I to the fourth times I, which is 1 times I, so that gives me I. Okay, and this pattern of I, -1, -I, and 1, this is going to repeat, right? Every 4 units or every 4 I's. Okay, so if we wanted to know what I to the 17th was, right, we would take that 17 and we would divide it by 4, which gives me 4 with a remainder of 1. It's the remainder that we care about. So I to the 17th is going to give me the same thing as I to the first, which is I. Okay. Right? If I had, let's look at I to the 6th, right? I to the 6th, how could I write that? I to the 4th times I to the 2nd, right? And I to the 4th we know is 1. I to the 2nd is -1. So that means I to the 6th is -1. Notice how it repeated the pattern. I, -1, -I1, I, -1, right? I to the 7th is going to be -I. I to the 8th will be 1. Well, we could use our little shortcut here, right? I to the 6th. Okay, so let's do 6 divided by 4. That gives me 1 with the remainder of 2. The remainder is what we care about. So that means I to the 6th is the same thing as I to the 2nd, which is -1. So all we have to memorize is the first 4. And we don't even have to do that. You can kind of figure it out, right? You don't have to actually memorize it. You can figure it out. But when we get to let's say I to the, let's do 82nd, right? We're not going to figure it out. We're not going to write them all out, right? We're going to do 82 divided by 4, which is 20 with the remainder of 2. So this is equal to I to the 2nd, which is -1. Okay. Now, the nice thing is that you can do it on your calculator, right? So if you look at your calculator, you do have an I right here above the decimal point, okay? So right above the decimal point. So I'm going to do second I. Oops, let me clear that screen so I can give you more, so you can see it better. Second I to the power of 82, and that equals -1. Okay. Okay, because you have it. That's good. You have it in. Where is it on my calculator? You have it in complex number. If I can find that on this calculator. Oh, here it is up here. Instead of real, you have it like that.
more. So how do I do it?
So that's actually good to leave it like that.
Oh, okay, leave it how I.
Yeah.
Okay.
Oh, mine still didn't do it. But that's okay. That's putting it in standard form, which is what it should be.
Okay.
Okay. This is just a different version on here. Okay.
So if I got that, would I still just put like whatever my front number is? Like, don't add the +0.
You can.
It's right.
It's right either way. Okay. Okay. So these are imaginary numbers. Now, a complex number uses real numbers and imaginary numbers. Okay. So a complex number is going to be in the form of something like 3 plus 2i. Okay. Now there is a complex coordinate plane that you can graph these on, right? So how in the world do we graph 3 plus 2i? Oops, come on. There we go. First off, we have to find the right line here. There we go. Okay. So the complex plane, instead of being x and y, right, the complex plane is going to be the real number and the imaginary number, right? So 3 plus 2i, we would graph that. We'd go 3 on the real number line, 3, and then 2i, so 2 on the imaginary line. So there's my point, 3 plus 2i. That's my complex number graphed on a complex plane. It's actually very, very easy. Okay. One of the fun things with imaginary and complex numbers is what we call the Mandelbrot set. Now, unfortunately, we do not have the time to explore this, but I'm just going to show you very, very briefly because it's fun for some of you that are more artistic. Benoit Mandelbrot was a mathematician that kind of played around with the complex numbers. And what he did is he took the distance between complex numbers. And remember, distance is the square root of distance in real numbers, right? Distance in real numbers is the square root of x2 minus x1 squared plus y2 minus y1 squared. Well, Mandelbrot did that using imaginary numbers, and then came up with a set of numbers that when graphed give you what we call a fractal. Have you heard about fractals? Okay, gives you a fractal. So let me just show you some examples of fractals. Fractals are really cool. Let's see, images. Okay, this is the most common. This is the fractal created by the Mandelbrot set. Okay, for those of you that are really artistic minded, you'll like this. For those of you that are, excuse me, computer focused, cold, right? The way that these occur, what happens with these fractals or with any fractal is that it is a recursive procedure. What's a recursive procedure? Okay, recursive procedure means when you get an answer, you're taking that answer and you're plugging it back into the same formula again. So for instance, let's say that we had, I'm just going to make it very, very simple. Let's say that we had f of x sub I, okay, is equal x sub I plus 3, right? So when x is equal to 0, f of x is going to be 3, okay? So then what makes it a recursive procedure is that the next, right, x sub 1 will be 3. So now f of 3 is going to be 6. Okay, when you start doing arrays, Cole, which you'll do this semester in computers, you'll be doing this type of thing, okay? And that's what's going to help you with that program on the calculator that you were trying to do. Okay, so here now the next x value becomes 6. X sub 2 is 6. So now f of 6 is going to be 6 plus 3, which is 9. This is what's called a recursive procedure. You're taking the result from the previous one, and that becomes the new entry value, right? So, remember how Cole was working on his calculator? What program was it you were working on, Cole? Factoring, right? So, and where were we running into trouble?
Synthetic division.
Okay, so in synthetic division, right, we had every time you do something like, let's say 3, and you got, 1, 2, 4, 6, right? You've got to take whatever the value is and add to it, and then again multiply, and then add, right? And we keep doing that. We keep doing the same thing, but with a new number. That's a recursive procedure, okay? Well, Mandelbrot did that with imaginary numbers, right? Or with complex numbers. The cool thing about a fractal is that it's the same throughout. Let's see if I get a bigger picture here. We're limited with our technology in being able to see it at a certain point. Yeah, I wanted a bigger picture. Okay. If you were to zoom in to this, you can see just from what you're looking at, each smaller piece is the same shape as the larger piece, right? It's all these smaller pieces within, they're all the same shape, right? These are all just cool variations of fractals, right? And if you were able to zoom in, you'd see that they are all just the same shape as the original. But of course, we're a little bit limited with our technology. And of course, this is just some cooler coloration. The original Mandelbrot set fractal basically used one color when something was true and one color when it was false. And that's how we got the really cool looking colors there. What I love about fractals and about the whole idea of fractals is that they occur in nature all around us. Okay, different flowers, pine cones, ferns. So as you look around nature, like so this, if you look at it, all the inside little pieces are the exact same shape as the bigger pieces. Okay. Okay, these are all just examples. Okay, let me just pull up fractals in nature. And I wish that we had time to explore this more. But here's a fern. It's just, God is a God of order, right? God loves mathematics. Mathematicians love God, right? God is a God of order. That's not an accident that these things in nature have such order to them and that they have such symmetry to them, right? It's not an accident that a fern looks like this and that its pieces are all the same within, right? Snowflakes, another really good example of fractals. How about a peacock, right? So these are all fractals because of the recursiveness of what it's made of, okay? Okay, end of our sidetrack. Okay, complex numbers. So complex numbers, standard form, something like 3 plus 2i. We can add complex numbers, okay? And it's very, very simple. We're just combining like terms. The 3 and the 4 are both real numbers. 3 plus 4 is 7. 2i minus 6i, what do you think that equals? Negative 4i. And that's our answer. Okay. Adding and subtracting is very easy. So if you look at number 1 on that worksheet, we have 3 minus I plus 2 plus 3i. Okay. Adding our real numbers, we get 5. Adding our complex, our imaginary numbers, negative I plus 3i is plus 2i. Okay. Make sure that your answer is in the A plus BI standard form. It would be incorrect if you wrote 2i plus 5. That would be incorrect. It has to be in the 5 plus 2i. Because when we graphed it, right, we graphed it, we went 5 and then 2i. Right? If I write it the other way, that's going to make it difficult to graph. Okay. So the standard form should be in the a plus 2i. Okay, we can multiply 4i times I. So just like if this was an x, right? If this was 4x times x, what would we get? 4x squared. So 4i times I is 4i squared. Okay? Now the only thing is we never want anything above just an I. So we never want I squared, I to the third. And if we look back, right, everything can be reduced down to a 1 or an I. Okay? So what we're going to do, we have this I squared. What does I squared actually equal? -1. So it becomes 4 times -1, which is -4. Okay? Does that make sense? Okay. Let's look at 5 plus 2i times 5 minus 2i. I want you to try and do this one by yourself. This is on the worksheet I gave you. Okay? Try to do this one by yourself now that you have a little more information. Okay, so Anthony, tell me what you got when you FOILed.
29.
Tell me the whole thing, right? Before you simplify it.
I got 25 plus 4.
Okay, so we're going to FOIL, so we get 25 minus 10i, right? And then plus 10i. And then minus 4i squared, right? So, of course, the minus 10i and the plus 10i will cancel. So we have 25 minus 4i squared. What's I squared equal, Bella? -1. So 25 minus 4 times -1 becomes 25 plus 4, which equals 29. Okay. Try another one? Yes, please, Mrs. Murray. Yes. Okay, let's do 3 plus 2i squared. So the first thing I'm going to do is rewrite this as 3 plus 2i times 3 plus 2i. And then, Nick, what do we do from there? Yeah, how do we multiply? Foil it, yes, we're going to foil it. Okay. Okay, Jack, when I foil it, what do I get?
9 minus 12i plus 4i squared.
Where'd you get the minus 12i? Did I copy it wrong?
Plus 12i squared.
Okay, so we're going to do 9 plus 6i plus 6i plus 4i squared, right? Or if you recognized this perfect square trinomial, you could have skipped a couple of steps. 9 plus 12i plus 4i squared. Now what?
That will become a -4.
Right. This becomes a -1. So we have 9 plus 12i plus 4 times -1. So Mason, you're right. We try to add like terms, but when we look at it, we don't actually have any like terms, right? So now I've got 9 plus 12i minus 4. Now I have like terms. 9 and minus 4 is 5 plus 12i. And we leave our answer just like that. Can't do anything with the I. Okay? So that's our answer. How are we doing? Give me a fist to 5 on how you feel. Okay, let me give you one more to try. Let's do 4 minus 5i times 3 plus 2i. Have you do that one. Okay, so we're going to FOIL again. 4 times 3 is 12. 4 times 2i is 8i. Negative 5i times 3 is negative 15i. Negative 5i times 2i is negative 10i squared. Right? I'm treating it just like I would if it was an x. Okay? All right, so now I'm going to combine what like terms I have. So 12 minus 7i, right? So I combine these two like terms, minus 10, and instead of I squared, what are we putting there? Negative 1. So this becomes 12 minus 7i plus 10i. Oops, not I, sorry about that. Okay, so this becomes 22 minus 7i. Notice that I did not write negative 7i plus 22. This would be wrong. It has to be in the standard form of a plus bi. I should say plus or minus, right? Okay. Question so far? Okay, we're going to do division. Okay, how much time do I have left?
You get out at 9.
Time too. Good. Okay, we're going to do division. So we have 2 plus 3i over 4 minus 2i. Okay. Now, before we do that, what would we do if this was a 4 minus 2 square root of 3? Or let me just make it even easier. If it was just 4 minus the square root of 3, what would we do? Multiply by 4 plus the square root of 3. Remember, what was that called? The conjugate? Did we talk about the conjugate? Conjugate it out of the denominator, right? Remember the conjugate? Arnold Schwarzenegger math? Conjugate it out, right? So we're multiplying by the conjugate. This is a square root. I is a square root. We need to get rid of that square root. So how do we do that? We're going to multiply by the conjugate. What do you think the conjugate is? 4 plus 2i. Good. And we have to do that on the top and the bottom. Okay. Okay. So we're going to FOIL. This becomes 8 plus 4i plus 12i plus 6i squared. Right? This is not difficult, but it's tedious. You just have to take your time, one step at a time, right? Down here we get 16 plus 8i minus 8i minus 4i squared. Okay. All right. So let's see what we can do up top. We have 8 plus, we can combine some like terms. So this becomes 16i plus 6 times negative 1. Right? Don't do too much at once until you get very, very good at it, because you'll make mistakes. Okay, we've got 16 Now we're going to combine like terms, so the 8i's will drop out. So minus 4 times negative 1. Okay. So we have 8 plus 16i minus 6 over 16 plus 4. That's going to give me 2 plus 16i over 20. Okay. Is that in the form of a plus bi? No. So I am going to rewrite this. So this is going to be 2 over 20 plus 16 over 20i. Everybody okay with that? All right, so now we're just going to reduce this. So this becomes 1 over 10 plus, let's see, 4. So 4 over 5i. Now we've got it in the correct form. Okay, so this is partially correct because it's not in the correct form. Okay, when you do these division problems, once you multiply everything out in the denominator, if you still have an I down there, then you did something wrong. The idea of multiplying by the conjugate is to get rid of the I. Okay, we're taking the I out. Okay. It's like the Christmas story. Anybody watch the Christmas story? You'll shoot your eye out. You'll shoot your eye out, right? He shot his eye out. He did. Okay, maybe not his eye out, but he hit his eye. Did you never see that movie?
I saw some of the movies scared of Santa Claus.
Yeah. The Christmas. Oh gosh, that's a little overkill there, but yeah. Okay, let's do 4 minus 3i over 2 plus I. Let me have you do that one. Okay. So remember, every time you have homework, you're going to have a mini quiz the next day. If you're absent, be prepared because you're still going to have a mini quiz. So make sure that you're doing your homework.